Well, hello, good people. Today we are talking about 2D force vectors. Now, so far we have talked about having multiple forces acting on an object, and we've talked about how to find the net force. But so far, everything that we've looked at has looked kind of like this. We've had some sort of object, we've had some forces in the y direction, and also some other forces that are acting in the x direction, things like friction, maybe is slowing it down, and maybe there's a force pushing it forward. And so far, everything that we have looked at has been kind of like really nicely spaced, where each of these arrows are fitting very nicely into either the y direction category or the x direction category. And so it makes our math very, very simple. We add up the forces in the x direction and we add up the forces in the y direction, and we write two net force equations. Well, today we're going to look at something a little bit different. Suppose that instead of having an arrow like this, where you're pushing the box straight to the side, suppose that instead you tie a rope to the side of this box. And when you tie a rope to the side of this box, you end up pulling up on the box at an angle as you pull the rope up and forward. Now, if I asked you to find something like, I don't know, the coefficient of friction between the box and the floor, or the acceleration of the box, could you do it? Let's take a look. These are going to be the type of problems that we are solving today, and we are going to start with one on page 141, and we're going to look at number 1. I actually am going to pull up a new page here because I want to have a full sheet of paper to really work through this problem. When I show you all the steps here, you will show all of these steps when you do this problem on a homework assignment or on a test, and you do need to show all of these steps in order to earn full credit. Take a look at page 141, question number 1. It says, a student pulls on a rope that's attached to a box of books and moves the box down the hall. The student pulls with a force of 185 newtons at an angle of 25 degrees above the horizontal. The box has a mass of 35 kilograms, and mu k between the box and the floor is 0.27. Find the acceleration of the box. Okay, we always start the same way. Step 1, draw a free body diagram. Step 1, FBD. We have a box here, like this. Yay. And, let's see here. The student is pulling with a force of 185 newtons at an angle of 25 degrees above the horizontal. I'm going to draw a force vector for the student's force like this. And this force, I'm going to call it FA, where A just stands for applied force. The force that the student is applying is 185 newtons. And the student is applying this force at an angle of 25 degrees above the horizontal. When it says 25 degrees above the horizontal, if this is the horizontal line right here, that means that the angle between the horizontal line, which I just made up with a dotted line, and the force here is 25 degrees. So we can label that here. Then we have the mass of the box is, what does it say? 35 kilograms. And mu k is 0.27. And we are looking for the acceleration of the box. Before we continue on, there are a few other forces we need to add to our free body diagram. For one thing, gravity is pulling down on this box, and so we will label Fg. Then, at the same time, friction is slowing this box down, so we will label Fk. And also, the normal force is pulling this box up, so we will label Fn. Okay. Now, before we move on, let's talk a little bit about oh gosh, sorry, we need to define our axes first. I'm going to say that up is positive y, and I'm going to say that to the right is positive x. Okay, now here's what we can see. FG and FN are clearly both in the y direction, and FK is clearly in the x direction, but FA is a little funky here. Do you see how FA is kind of in the y direction and also kind of in the x direction? This is where we are going to break this vector down into its component parts. Here's how we do it. I'm going to draw a diagram of FA off to the side so that I can draw it a little bit bigger here. This is FA, and we know that it makes an angle of theta with the horizontal. Well, what we can do is we can say that FA has an x component and a y component. The way that we show that is we say the x component of FA is just this little section right here. That's how far FA reaches in the x direction. So I'd write FAX here. And then if you go up straight like this, this is the height of the triangle that FA makes, and we would call this FAY because that is the y component of FA. So you can see that FA has two components. It has an x component and it has a y component. And when you combine together this x component and this y component, you get FA. Now, let's take a look here back at our diagram. When we take a look at our diagram here, we know, actually, wait, I'm changing my mind. We're going to start by writing net force equations, and then I want to go back and kind of edit our free body diagram after we write our net force equations because I want you to see what's true. Okay, let's go ahead and start here. Once you draw your free body diagram, that's step 1. Step 2 is to define your axes. That's step 2. For these kinds of problems, step 3 is to break down each vector into its component parts. This is step 3. Now, step 4 is to write out the x direction and the y direction. Sorry, I'm going to redo that. Okay, let's see. We have our x direction and our y direction. And we are like maybe going to have enough space here and also maybe not going to have enough space here, so we'll kind of see how this goes. Okay. Okay, here we go. What we're going to do is we're going to write a net force equation in each direction. And here's how I'm going to do it. I look at my free body diagram and I say, okay, what forces are happening in the x direction? And here's what I would say. I'd start by saying my net force in the x direction is going to equal. Now I have two forces at play. One is the force of friction, which is slowing me down. So I'm going to write negative Fk. The other one in the x direction is a part of Fax, or is a part of Fa. It's Fax. Do you see how Fax is a part of Fa that is in the x direction? So I'm going to add in Fax because that is the x component of Fa and it's the part of the force Fa that is acting in the x direction. Now I can set this equal to my mass times my acceleration in the x direction. Okay, now let's take a look at the y direction. In the y direction, take a look at my forces. I have Fg pulling down, so that's going to be minus Fg. Then I have Fn pulling up, so that's going to be plus Fn. Then I have the y component of the Fa. The y component of Fa is just this little right here, or right there, and that part is helping to pull the box up. And that's going to equal the mass times the acceleration in the y direction. Now, here are some questions. First question, is there acceleration in the x direction? You should say yes, because it asks, find the acceleration of the box. Fa is going to cause the box to speed up in the x direction. When I'm looking at my vectors here then, that means that Fax, the x component of Fa, has to be longer than Fk, because the force pulling it forwards has to be bigger than the force slowing it down. I look at my diagram here and I say, that's true. If this is my Fax right here, then that is longer than my Fk, so that looks good to me. Then I look at my y direction. In the y direction, there is none acceleration because Fg is pulling down, Fn is pulling up, and Fay is also pulling up. Altogether, these add to make 0 net force and 0 acceleration. I know that there is 0 acceleration because this box right here is not plummeting down towards the center of the earth. It is not shooting up towards the stars. No, it's staying right where it is on the floor. So the acceleration is 0, which means I can take this little guy here and go whoop, 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 and the acceleration is 0. That means I can rewrite this as negative Fg plus Fn plus Fay equals 0. Let's take a look at my free body diagram then. This means that my up forces have to add to cancel my down forces. Here, my down force is Fg, and my up forces are Fn and Fay. That means that the combination of, here I'll draw this in, the combination of this little bit of length here, this Fay, in combination with this little bit of length here, this Fn, if you were to add these two together, they should together equal the length of Fg. Right now you can see that the way that I've drawn this, Fn plus Fay, that's actually a little bit longer than Fg. So what I'm going to do is I'm going to make some adjustments to my diagram. Here's going to be the adjustment that I'm going to make. I'm going to make Fn smaller. The reason why I'm going to make Fn smaller is because in real life, the normal force actually is smaller in this situation. Remember that the normal force is the pressing force. It's how hard that box presses down on the ground. If there is something that is helping to lift the box off the ground just a little bit, well then the box won't press as hard on the ground and the ground won't press up as hard on the box. You can imagine it like this. Suppose that you are a little ant in between the box and the floor. And suppose that someone came along and applied this force Fa at an angle. Would you, as a little ant, today is payday goodies.
Come on down. Bring your mug if you want a coffee.
Okay. You could imagine that if you were a little ant sitting underneath this box and someone came along and applied an Fa and lifted that box up just oh so slightly, you would say, whew, I get a little bit of breathing room because that box is not pressing down on me as hard. That means that the normal force just shrank. It just got smaller. So the normal force is now not going to equal Fg like it did in the last problems that we've done. Now the normal force is going to be less than Fg. Before you move on, please check and make sure that you understand why that's true, that the normal force is going to be less than Fg in this case. Okay, next, I have two equations going here. I have negative Fk plus Fax equals mass times acceleration in the x direction. And I have negative Fg plus Fn equals, or plus Fay equals 0. Now here's the next step. The next step is step 5. And step 5 is plug in equations for any forces that we can. Okay, let's start with Fk. Fk we know is negative mu k times, I'm going to need more space here. In this case, it's negative because we got a negative sign in the front when we took care of our direction. But it's going to be negative mu k f n. Then let's look over here. This FG, because I don't have FG, I'm given a mass, I can turn this FG into mg. So I write it as mg like this. The normal force, I do not have an equation for, so I just write it as Fn. Now let's take a look at FAX and FAY. I don't have FAX and I don't have FAY, but I do have FA and I do know this angle. Hey, could you use a trig friend to help you solve this problem to find FAX? Absolutely you could. You would say that FAX here, sorry, my work is kind of chaotic here, but you would say that FAX, if I look at this angle, I'm thinking, I got the adjacent here and I know the hypotenuse, I'm going to use cosine. And we know that cosine of theta is equal to FAX over FA. Rearranging for FAX gives me FAX is equal to FA times the cosine of theta. Okay, now I have an expression for FAX. Let's see if we can find an expression for FAY. Let me move this guy out of the way. Okay, taking a look here at FAY, if I were trying to find FAY, here's what I would do. I would say, well, that's an opposite. I have a hypotenuse, and I know theta. I'm going to say that sine of theta, sine of theta is equal to FAY all over, I just really did bad stuff there. Let me try to fix that. Oh gosh, I'm embarrassed. You're impatient. I get it. Actually, no, you would never be impatient. You're very patient, which is a good thing, because if you had no patience, then this would be the point where you probably hate me forever. Okay, so FAY all over FA. Great. Now, if I want to find FAY, I go FAY is equal to FA times the sine of theta. Now I have two equations, one for FAX and one for FAY. I can then plug these equations back up into our statements over here. So I can plug in here plus FA times the cosine of theta is equal to MAX. And here I can plug in plus FA sine of theta is equal to 0. Okay. Next, step 6 is to rearrange and solve. At this point, we have done all of the physics work that we really need to do. The rest of the work that we're going to be doing is really mostly just algebraically rearranging. Let's take a look. I am looking for this acceleration here. In order to find this acceleration, I know mu k, I know Fa, I know cosine of theta, I know the mass, but unfortunately I do not know Fn. So in order to find Fn, I have to go into the y direction to find it. Rearranging in the y direction for Fn gives me mg minus Fa sine of theta. Hey, pause here. Does this make sense to you? Do you see that that means that Fn is equal to the weight, but it's the weight, mg, minus the y component of Fa? That should make some sense to you. You should say, yes, that's exactly what it should be. It should be the weight minus this little section here. That's what should give me Fn, because Fn would equal this minus this, since these two have to add together to equal this. Okay, now I'm going to plug Fn back over into, not there. Oh, you could do it. I'm going to plug Fn back into the other side here. When I do this, I'm actually going to get rid of because I'm kind of running out of space. You could continue to do your work in the x direction, but I'm going to now rewrite this whole big equation down here. So now I have a statement that looks like this. I have negative mu k times mg minus fa sine of theta plus fa cosine of theta is equal to max, like this. And my very last step here is to rearrange to solve for ax by dividing both sides by m. Now, I get that ax is equal to negative mu k times mg minus fa times the sine of theta plus fa cosine of theta all over m. And now we are good to plug in numbers. And I'm going to pause here real quick because I actually need a calculator and I don't have it here with me. So 1 second, team. Okay, now with my calculator, when you type all of this in, which you should show before you type this into your calculator, you should show a step with all the numbers plugged in. I won't do that here because I'm kind of running out of space, but you definitely should. I feel like my size is bad here. Yes, it is. When you type this into your calculator, this is still not working. Come on, you can do it. Yes. When you type this into your calculator, you should get positive 2, that's an equal sign, positive 2.7 meters per second squared. Do include a positive sign here to include direction. Do include good units and good sig figs. Okay, and that is one problem. Let's go ahead and take a look at another one now. I'm going to go ahead and get this pulled up here. We're going to take a look at question number 4 on page 141. So that was number 1 on page 141. Now we're going to look at page 141. Wait for it. It's loading. Okay, now we're going to look at page 141. Page, yes, number 4. Okay, here's the situation. It says a box of books weighing 325 newtons moves at a constant velocity across the floor when the box is pushed with a force of 425 newtons exerted downward at an angle of 35.2 degrees below the horizontal. Find mu k between the box and the floor. Okay, let's start by drawing a free body diagram. When I draw a free body diagram, I have this box here. I'm going to start by drawing the force that the book described. It said that there's a force that's applied that's downwards, and it's applied at an angle theta of 35.2 degrees. Oh, wow, that's a terrible theta. 35.2 degrees below the horizontal. Okay. We also have the weight of the box pulling it down. And we have the force of friction slowing it down. And we have a normal force from the floor pushing it up. Now let's talk about the size of each of these forces. First, let's look in the x direction. When I read this problem, there were 2 words that popped out at me and stared me right in the eyes, and those 2 words were constant velocity. I'm saying constant velocity, that means that I have none acceleration. That means that all of my forces in the going to the right have to cancel out with all my forces going to the left. When I'm thinking about this in my brain, that says to me, okay, if I have, I'm going to use a light blue here, a cyan, excuse me. If I have this as my FAX, then my FK, which I forgot to label embarrassingly, then my FK has to be equal in size to FAX so that the two can cancel out perfectly. Right now, I'm looking at this diagram and I say, that doesn't look quite equal in size. So I say, I shall make some modifications. And I'm going to make my FK slightly longer here. Pretend that you can see the arrow on the other side. Now, I take another look here. I'm going to go to red, but the light red. I suppose you would call that pink or red 300. Okay. Here's what I'm looking at next. I'm looking at the y direction, and in the y direction, I see that I have FG pulling down, and also, because this student is pushing downwards at an angle, you also have FAY is negative. That means that FN has to cancel out both FG and FAY. And so FN has to be equal in size to the size of FG plus the size of FAY. Eyeballing that looks to be about this long, so I'm going to draw FN up about this long. Notice FN is longer than FG, and that is the correct way to draw this diagram. Then I would draw positive Y and positive X. I would identify those. Then I'd write down all of my knowns and unknowns. My knowns and unknowns here, I have FG is equal to 325. Sorry, that says FG is equal to 325 newtons. Then we have FA is equal to 425 newtons. We also know the mass of the box is 35.0 kilograms. No, gosh, I'm mixing it up from the last problem. Forget that I even said anything. That's just literally not even true. The problem just super does not say that at all. Wow, that was embarrassing. But you know what it does say is it does say that the angle here is 32 point, nope, not that. I got to learn how to read a textbook. It just is seeming really important the further and further we go. Oh no, I have the working sign of death, which means we might have to pause the video. You can do it. Keep working. Keep working. Oh, yes. Okay, good. Sometimes it just starts working and it never stops. Okay, 35.2 degrees. And we also know, because we said constant velocity, that the acceleration is 0. You do not have to give this given here. I like to write it so that I remember my situation. And finally, last but not least, I'm looking for mu k. To start this problem, I would divide things up into the x direction and the y direction. Here's my x direction, and now I need a y direction. Oh, here is a great debate of the day. If you had to choose one to be blue and one to be red, do you think the x direction is more blue or more red? And do you think that the y direction is more blue or more red? Anyway, you can all argue that one out amongst yourselves. Okay, here we go. We divide it up like this. Actually, that's way too long, so I'm going to trim that down a little bit. Okay. Sorry, everyone. Okay. Now, we'll start by writing a net force equation in the x direction. In the x direction, my net force, my net force in the x direction would be positive FAX, that's just the x component of FA, minus FK is equal to my mass times my acceleration in the x direction. Now, because this little guy is going at a constant velocity, I can start here and say, whoop, that's 0. Now in the y direction, we got it. In the y direction, I would say that the net force in the y direction is equal to, check it out, I have positive Fn, negative Fg, and also negative Fay, because Fay, the y part of A, is going down. And that equals the mass times the acceleration in the y direction. Now there's one last thing that I want to show you here, and I'm actually not going to finish out this problem with you. I will allow you to try to finish this problem on your own. But one last thing that I want to show you here. You could and should take a little second and off to the side write things like, yes, I could find Fax, and Fax would be Fa cosine of theta based on my diagram. And then you could look off to the side and you could find Fay, and you would say, yes, I think that Fay would be Fa sine of theta. So you could do that and you could plug that in. You could also plug in for Fk, mu k Fn, but here's a question for you, is would you, when you start plugging things in here, would you plug in anything for Fg? And you should say, no, Miss Wilson, I wouldn't. I would leave Fg as Fg. And the reason why is because you're given Fg. We change Fg into mg if we're given a mass and we need to find the weight. But I was already given the weight, so I don't need to do anything here. I can just leave it as an Fg, and I'm all good to go. Then what you would do next, your next step here would be to plug in these equations here and here, to plug in an equation for Fk, then to rearrange to solve for mu k. You would probably need to find Fn in the y direction and plug it back in over in the x direction. And that's the problem. And that is all for today, folks. Today we looked at how to solve problems with two-dimensional force vectors. So, yeah, that's pretty much it. I really don't have anything more for you. The next time when you come back, we'll be taking a look at ramps and how two-dimensional force vectors work on a ramp. I'll see you then. Bye, good people.